Okay, so let me continue with the slide. So here, as I remember, we have more or less here. We can discuss the advantages of direct energy depositions using the electron beam as a heat source, and we focus only here the methods at feedstock materials. So for the case of direct energy deposition using electron beam as heat source, we have high deposition rate with the rate of around about 7 up to 18 kilogram per hour. It has the ability in order to use with wide range of materials. Especially, it's good to use the available wire alloys because it's cheaper comparing to the case of the rare alloys with a limited number of suppliers. So you may see that the price would be so expensive for the rare wire alloys. And the deposition parameters. The direct energy deposition using electron beam can create a large vacuum chamber built environment. So in other words, you can fabricate large structures. So because everything is limited within the building chamber. So the larger building chamber, you have the larger the part. Especially for the electron beam, you should maintain the vacuum inside the building chambers, and therefore you should create uh, a volume. Uh, how can I say? Closed volume. You should have a closed volume. So in order to maintain the high vacuum inside. So the high purity vacuum of 1.3 10 to minus 5 millibars. So 1 bar is equal to 0.1 megapascal. Yes. So it's not familiar here in Vietnam, but in European countries. So, for example, the hydrogen gas, uh, they, uh, they work at 350 bar or 35 megapascal or 70 megapascal, which corresponds to 70 megapascal. So 1 megapascal equal to 10 bar or 1 bar equal to 0.1 megapascal. Yeah. Okay. And limitations of direct energy depositions using electron beam as its source. Yeah, the machine may be the largest and the most expensive 3D printers because it is the system associated with the generation of electron beam. Yeah, the heat is built up in the part. Yes. So and surrounding is a vacuum, and it's quite difficult, to dissipate the heat. Or heat can be easily built up inside the part. Yes. So you need, since the heat is accumulated inside the pot, and you need longer cooling time. And with the longer cooling time, it means that the temperatures of the pot is still high. So the atoms inside the pot receive the free give energies, so the high free give energies, which promote the diffusion of the atom inside the pot and between the grain, which made the grains grow. and and therefore larger grain, lower strength of the part, because you know that when the grain is more, or when grains are more, and you have the within a fixed value volume, small grains, this means that you have the larger number of grains. larger number of grains Larger number of grains, it means that you have larger areas regarding the grain boundaries. And the grain boundary is the reason why you have the disorders of the atoms, because there you do not have the clear directions of the lattice structures of the lattice. Yes, of the lattice. And therefore this area, if it is high, and is provide the strengthening mechanism for the part. Or you can see from the Hunchback equations, you could see that if you reduce the diameter of the grains, and then you could have the effects of strength enhancement. Hunchback equations. Yes, and probably I will introduce during the course, but not in this chapter, but the other chapter. I did not remember exactly, but it can be in the in the course of aerospace material or in the course of additive manufacturing. Hunchback equations. So it's quite a fundamental equations showing the relation between the diameter of the grains and the strength of the material. It's difficult in order to control the large melt pools, of course, and restrict to flash depositions. Yeah, and seen comparing to the case of butterbath fusion, you have poor surface quality comparing to the case of butterbath fusion, and therefore even with butterbath fusion, you still need the post-processing in order to enhance the surface quality. And for the direct energy deposition, you need, yeah, for sure, you need the post-machining in order to improve, yeah, or to smooth the surface of the part after the 3D printing process. Large base feature, yeah, I'm sorry. You need to control the effect of shrinkage or distortion, yes. Yes, because the heat is high. Yes, and since the heat is accumulated inside the part, and you may have the residual stress, and this may have the negative effect in terms of distortion. Okay, and it can be briefly summarized in the figure on the top right figure, and you can see uh, very briefly the disadvantages of using direct energy deposition with electron beam as heat source. So the idea is similar to the case of using laser as a heat source. Yeah. So locally melt uh, the material at the position that the material will be deposited to. The material can be the wire or can be the powders. So it will be locally melt at the spot. Yes. And the material will be formed spot by spot, layer by layer. I'm sorry, line by line, and layer by layer until we fabricate completely the 3D physical object. Yeah. Now, now we have talked with some advantages and limitations of another direct energy deposition technologies, but these technologies employ plasma arcs as the heat source in order to melt the feedstock material. So advantages. So there are three remarkable advantages of using plasma arc. First, we have the high deposition rate of several kilograms per hours. In other words, it has high material efficiencies, almost no defect, and low pass codes. So especially in the case of density, we were talking about the, the porosity inside the part is still the limitation of several types of technologies like bizetting or in the case of Photoback fusion. But with using plasma assisted direct energy depositions, so you almost have no defect, no porosity, and relatively low pass codes comparing to the past made of the same material, made of the similar materials, but with traditional manufacturing technologies. So lower, relatively low pass codes comparing to the case that we apply we use the similar or the same materials. We yeah, but we apply different fabrication technologies with respect to the direct energy deposition. There's an ability to produce the large near-net shaped parts to reduce scrap. So this is the advantage of almost all 3D printing technologies where we can fabricate the near-net shaped components. So when we're talking about the additive manufacturing, we can save the material via we are fabricating the near-net shape part, so there's no need to cut a lot of material after the 3D printing process. Yeah, there's no need. However, it's quite difficult, to fabricate the part which is really complex, and is just restricted to be used to fabricate the part with low to medium complexity. So we may have the extensive distortion. So the part is distorted, and the negative effect is the large grain. The grain grow owing to the slow cooling rate. Yes. So you may remember that on Tuesday we have talked about the effect of the cooling rate on the microstructures that can be formed after the heat treatment processes. And if we cool down the parts slowly in such a way that the diffusion can occur, and we have the microstructures which is occur on the binary phase diagram, for example, the iron carbon binary phase diagram. And the diffusion process occurs mean that the atom can diffuse from one position to another position, from one grain to another grain. So it means that the effects, we can have the effects of grain growth. The larger grain can continue to grain, and the small grain will disappear. So, and that's why we have the grain growth. And the grain growth means that the boundary of the grains, the numbers of boundaries, grain boundaries will be reduced. So this means that the strength will be reduced. So that's why we see that when we have the grain growth effect, we have the and this can be considered that one of the limitations of the process. And similarly, you can see that the plasma, yes, will create extremely high heat. Yes, the temperature is I do not remember exactly. There are 4,000 degrees C. Yeah, and quite high temperatures. So and therefore, yeah, it's quite difficult, to fastly cool down the part. Yeah. So I just want to highlight a little bit about the NOS. NOS is Norwegian. So this is Norway in English, Norge in Norwegian, and NOS is tiếng Na Uy, yeah, người Na Uy. This is the name of the company, NOS Titanium, and they have a patent process called NOS Rapid Plasma Depositions. So this is a patent which have already registered in America. And this process employs the titanium wire as the feedstock materials, and the process and the system will melt the titanium wire in argon plasma with the argon plasma to build the near-net shape 3D object. And after you create the 3D object, so it's necessary to post-machine the part in order to finally form the aerospace part. So you can see on the right side, the upper figure. So you have the feedstock material is titanium wire. We have the rapid plasma deposition torch. Yeah, torch, not đuốc. Inside you have the argon gas. You have the tungsten electrode. Tiếng Việt là điện cực wolfram, phải không ạ? Điện cực wolfram có khí argon ở trong. Thì cái đầu đốt này, cái ngọn đuốc này nó sẽ tạo ra cái vùng argon plasma có nhiệt độ rất là cao ở trên cái bề mặt của trên cái lớp layer mà chúng ta cần deposit cái vật liệu là titanium. Và cái NOS titanium này thì hiện tại là vận hành chủ yếu là chế tạo ra các cái sản phẩm mà làm bằng titanium. Thì tôi nói luôn tiếng Việt nó nhanh. Thì những cái sản phẩm của họ ấy thì nó có cơ tính là cao tương đương so với cơ tính của những cái vật liệu gen dập mà làm bằng titanium, có nghĩa là nó có độ tin cậy rất là cao. Nó gần như là không có các cái khuyết tật, và các cái sensor của họ nó có thể detect được nếu tôi nhớ không nhầm là khoảng 600 cái data trên một giây. Trong cái quá trình chế tạo, trong cái quá trình mà gia công như này thì những cái sensor của họ có thể thu về những cái lượng data là 600 cái điểm data trên một giây, để nó đưa vào cái việc xử lý dữ liệu và tạo ra cái điều chỉnh ngay trong quá trình mà nó deposit vật liệu như thế này. Nó cái processor nó sẽ xử lý làm sao cho tìm được cái tổ hợp các cái parameters tối ưu để tiếp tục deposit kim loại, nhằm đảm bảo là cái chất lượng kim loại là cao nhất sau cái quá trình deposition. Thế thì về bản chất thì nó là cái quá trình hàn thôi, hàn từng cái lớp vật liệu một, và chỉ những cái cross section nào, đúng không ạ, chúng ta cần thì chúng ta mới deposit vật liệu lên trên đó. Thế thì do cái quá trình nó là quá trình hàn, cho nên là các bạn thấy là sau khi mà tạo ra được cái vật liệu ở trên cái building substrate ấy, cái tấm substrate ấy, thì chúng ta thấy là nó rất là thô, đúng không ạ, nó rất là thô, và các cái bề mặt của nó thì có cái roughness thì nó to, nó rất là lớn rồi, không phải bàn rồi. Ngay cả cái hình dáng nó cũng không đảm bảo được cái hình dáng của cái chi tiết. Thì sau cái quá trình mà deposit cái vật liệu thì người ta sẽ tiến hành quá trình cutting, đúng không ạ, để chúng ta tạo hình lại cái vật liệu, tạo được đến cái chi tiết cuối cùng, đúng không ạ. Thì chúng ta thấy là nếu mà đem so sánh với cái phương pháp gia công truyền thống là tạo nên một cái thỏi đúc xong rồi cắt rất là nhiều vật liệu để bỏ đi, thì cái phương pháp gia công sử dụng direct energy deposition với nguồn nhiệt là cái plasma này, dạng vật chất thứ tư này, thì chúng ta có thể là tạo ra cái near net shape part, và sau đó thì chúng ta chỉ cần gia công loại đi một cái lớp nhỏ cái vật liệu ở bên ngoài thôi, thì chúng ta tạo được cái chi tiết cuối cùng. Và như vậy thì chúng ta xếp rất là nhiều vật liệu, chúng ta xếp rất là nhiều cái năng lượng cần thiết cho quá trình gia công cắt gọt sau đó, đúng không ạ. Bởi vì ở đây chúng ta cái quá trình cắt gọt sau đó nó rất là nhẹ nhàng, thì chúng ta sẽ xếp được năng lượng cho quá trình cắt gọt. Nếu đem so sánh với phương pháp gia công truyền thống thì ở dưới này chúng ta cũng có thể nhìn thấy một cách rõ ràng là từ cái S-build part, có nghĩa là cái chi tiết nằm ở bên tận cùng bên tay trái, cho đến cái chi tiết final part, thì nó rõ ràng là chúng ta nó là near net shape component, nó gần với hình dáng của cái chi tiết cuối cùng rồi. Chúng ta chỉ loại bỏ một lớp kim loại, một ít lớp kim loại thôi. Và trong cái quá trình post processing đối với hình ở dưới cùng ấy, thì các bạn có thể thấy là người ta có thể tạo nên cái lỗ bằng phương pháp khoan hoặc là đột dập chẳng hạn, thì nó đều có thể tiến hành ở trong các cái post processing steps. So comparing to the traditional manufacturing process, in order to fabricate, for example, titanium parts, the cost can be reduced from 50 up to 70% comparing to the forging process. This means that you reduce the weight, so you reduce also the machine energies, and that leads to say we reduce the time to market, and because you save the fabrication time and you save the time for developing the parts, and therefore you reduce the production lead time or time to the market of the part. And the buy to fly ratio can be greatly enhanced using the rapid plasma technologies. Yes, and you know that when you reduce the part of the many parts inside the aircraft airplane, and then you can carry more passengers, or the freight, or cargo, or in other words, enhance the efficiency of fuel consumption. Yeah, for sure, because you make the aircraft lighter. Yes, these the technologies which is developed by Norsemen, Norwegian people, and there's two branch. One branch, the headquarters is in it is I don't remember exactly, Raufoss. Yeah, One headquarter is in Norway and the other is American. So the next slide highlights the summary of different AM technologies and the key application of additive manufacturing. So 1, 2, 3, 4, 5, 6, 7. Yeah, 7 AM technologies. So you can see the brief summary here. Yeah, you can learn by heart if you want. Yes, it's not compulsory. It's not compulsory. But it's good to know. It is good to know. Yeah. The key application of the AM. So the AM additive manufacturing can be used in the different industry. For example, car industry, aerospace industry, in the medical industry, sport industry, and construction industry as well. And for us, we pay more attention to aerospace industry, where we can produce accessory of complex with complex geometry. There's possibility to control the density and mechanical properties of the part made of additive manufacturing technologies, and you can produce lighter accessories. So it means that you contribute to making the airplane lighter in the future. So if you could use the additive manufacturing with the structure optimization in order to design different types of spare parts in the aircraft. And for the car industry, so I think that one of the slide, one of the video that I showed you highlight the fabrication process for the Bugatti car brake caliper. Yeah, so this is one of the example for the car industry. But this is a luxury car. This is a Bugatti, so which is cost around more than 1 million euros. It's quite expensive. And for the medical industry, yeah, it can be used for fabricates, for example, for the dental implant. This can be used to fabricate several kind of fixture structures. Can be used to stem cell, fabricate stem cell for the hip prosthesis. What we call in Vietnamese stem cell, nó như kiểu một cái phần khớp xương háng ấy, là người ta sẽ in bằng cái vật liệu có thể là titanium này, có thể vật liệu là thép không rỉ này. Thường là titanium nó sẽ prefer hơn bởi vì nó là biocompatible, nó tương thích với cả cái vật chất bio, tương thích với cả cơ thể người, nó không bị đào thải ra. Thế thì sau khi mà in xong thì người ta sẽ cấy ghép vào cơ thể để cái bond tissue, những cái mô xương ấy, nó sẽ phát triển, nó bám vào cái stem cell đấy, và nó cũng có thể dùng để in ra cái acetabular cup ấy, là cái khớp háng luôn. Thì nó là một trong những ứng dụng của cái anh AM ở trong cái lĩnh vực medical treatment. Tất nhiên là nhiều lắm nhưng mà tôi không nhớ hết rồi, đi vào một vài cái khía cạnh này thôi. Còn trong cái lĩnh vực sport thì tôi không nói, nhưng mà construction thì chúng ta thấy là ở Hà Lan thì người ta xây bằng hẳn cái cầu bằng kim loại, đúng không ạ? Nó sử dụng phương pháp in 3D. Ở đây là in sử dụng cánh tay robot, thì nó tựa như là cái direct energy deposition, nghĩa là vật liệu mà deposit lên đầu thì cái nguồn nhiệt nó sẽ irradiate, nó sẽ chiếu vào đến đó để cung cấp nhiệt để nung nóng kim loại và nó solidify, và nó tạo ra cái layer, từng layer một, và cuối cùng là 3D object. Tất nhiên là bây giờ thì xây dựng nhà bằng các cái vữa hoặc là bê tông dùng công nghệ in 3D thì nó cũng không phải cái gì nó quá mới, nó cũng đang được phát triển ở một vài quốc gia trên thế giới rồi. Tuy nhiên thì vì nó đang phát triển cho nên là cái reliability, cái độ tin cậy của nó, đúng không ạ, thì chúng ta cần phải nghiên cứu thêm để đảm bảo rằng cái độ tin cậy, phải đảm bảo nó được tiêu chuẩn hóa, đúng không ạ, test trên tất cả các điều kiện rồi mới đưa vào cái thị trường của chúng ta được. So one of the last slides in this chapter we describe the summary. Just remember, one up is not one. Summary of sustainability advantages and challenge for AMs. So when we introduce the AM to the industry, so there will be several kinds of advantages when using the AM and challenges for using the AM as well. So everything had two sides effects. And let's briefly discuss more or less at till the end of the more or less at 10 to 2, and then we try to finish this chapter before 2, let's say before 2, and afterward we can talk about the chapter 2, chapter 2, where we focus on the understanding the method for additive manufacturing. Okay. And before this, do you have any question? Okay. No, I know. The test is coming. Yeah, advantages. So firstly, we focus on the product design, redesign process, because you know that is not the newly development process. Why? Because for the moment we are talking about the structural optimization. So we should have the original structure first. Since the original structure is not so optimized, and therefore we can optimize the structures. Or in other words, we redesign the original structures in order to optimize it, to enhance the performance, to reduce the weight, for example. So this is why we can use the term redesign process for the original structures in order to optimize its performance or improve the performance of the part via the use of additive manufacturing. And why? First, we can apply design freedom. So AM, additive manufacturing, can fabricate the free form part. So there's no restriction in terms of the geometrical complexity. So for the traditional manufacturing process for extremely complex parts, do you see that if we apply the traditional method to fabricate the part, and then the price of the parts will be high? Yeah, for sure. But for the additive manufacturing, there's no restriction regarding the complexity of the part. In other words, you can design it freely. So for example, if you drill the part, so you have the cylindrical shape like this, and you have the drill tool. So the only thing you can do is to drill and to create the horizontal cylindrical shape, the hollow cylindrical shape, or the hollow tube inside. So let's say if we want to create the tube inside, but in the helical shape, like a spring, then by drilling or the manufacturing, traditional manufacturing process, you cannot use. This cannot be used in order to fabricate this kind of internal channels, kind of helical internal channel inside. Yes, and yes. So this means that if you tend to use the traditional manufacturing process, the design process must address the manufacturing process. So you must design something that the manufacturing process can be used to process. Nói tiếng Việt cho các bạn dễ hiểu này. Tôi lấy ví dụ, nếu như các bạn đang thiết kế một cái chi tiết mà sử dụng phương pháp khoan để tạo hình chẳng hạn. Thế thì nếu như các bạn đã hướng tới cái phương pháp khoan này, thì cái quá trình design cái chi tiết nó cũng phải đảm bảo rằng là chúng ta design được cái vật liệu đấy ra, design được cái vật đấy ra thì nó phải dùng phương pháp khoan để nó tạo ra được. Thế còn nếu chúng ta design thế nào mà cái phương pháp khoan này không tạo ra được, thì có nghĩa là cái phương pháp thiết kế của các bạn nó sẽ không hướng tới cái phương pháp chế tạo. Cái phương pháp thiết kế bắt buộc nó phải hướng tới phương pháp chế tạo. Thế thì cái anh additive manufacturing nó hay ở chỗ là gì? Không cần biết phương pháp thiết kế của bạn là như thế nào, bạn design freely, gần như là với cái dạng hình dáng cấu trúc nào thì nó cũng có thể chế tạo được. Nó không bị giới hạn bởi cái technology limitation của cái anh traditional manufacturing process. Chẳng hạn như là dùng phương pháp khoan thì ta chỉ có thể khoan lỗ thẳng được thôi. Nếu mà chúng ta có hai channel, đúng không, nó giao cắt với nhau, hai channel giao cắt với nhau thì nó sẽ có cái intersection, có nghĩa là cái giao tuyến ấy, nó sẽ là cái cạnh sắc. Giao tuyến mà cạnh sắc ấy, thì nó sẽ làm tăng cái ứng suất tập trung lên, đúng không ạ? Thì nó với cơ bản thì chúng ta muốn làm thế nào chúng ta giảm được ứng suất tập trung thì chúng ta sẽ phải fillet nó đi. Nhưng mà fillet thì dùng cái phương pháp traditional manufacturing process như là khoan chẳng hạn, không thể làm được. Do đó là cái additive manufacturing thì bất kể cái internal channel nó complex như nào thì nó đều có thể in ra được. Use the biomimicry concept, so to mimic something, to mimic the bio concept, bắt chước lại cái bio concept thì cái này in English we call bio inspired design. So there's some kind of natural structures. Yes, we have very high strength, very high stiffness, and during the design process, we can design something which is bio-inspired. And by using the additive manufacturing process, we can fabricate the part which is have the bio-inspired concept. Yeah. Chúng ta biết rằng mẹ tự nhiên thì chế tạo ra những cái chắc structure, đúng không ạ, những cái kết cấu nó rất là ưu việt, ví dụ như kết cấu xương người chẳng hạn, nó không phải là đặc mà nó là kết cấu rỗng, chịu lực rất là tốt. Đấy, đó là chính là cái concept mà sử dụng rất là nhiều ở trong cái lĩnh vực thiết kế cho additive manufacturing. Có nghĩa là người ta dùng một cái chế tạo ra những cái chi tiết mà có cái cover, có những cái lớp ngoài thì nó là liên tục, đúng không ạ, nó như kiểu cái lớp da, giống như kiểu cái skin, nhưng bên trong ấy, thì nó không phải rỗng hoàn toàn mà nó lại có những cái support structure, có cái cấu trúc dạng lattice chẳng hạn, đúng không ạ, cấu trúc dạng lưới trong kim loại, cấu trúc dạng lưới ấy. Thì nhưng mà nó là 3D. Đấy. 3D thì nó sẽ hỗ trợ cho cái skin bên ngoài. Một mặt thì nó là chịu lực được, mặt khác nó làm giảm khối lượng đi rất là nhiều so với cấu trúc đặc chẳng hạn. Thì đấy cũng chính là cái bắt chước so với những cái concept tự nhiên, những cái concept bio mà mẹ tự nhiên tạo ra. Cái ý tưởng nó là như vậy. Optimize geometry. Yes, of course, I have already mentioned to you several times about the structural optimization or the geometry optimizations. So for the traditional design process, so we design and we fabricate. We use tree and arrow approach, and for several decades recently, for several decades ago, so we started to work with the FE simulations. Yes, or maybe a little bit earlier. We point out the reason inside the part with low stress. Yes, so with the optimization process, we can eliminate the materials at the regions having low stress under the influence of given load. Yes, so by eliminating the unnecessary materials, we optimize geometry. But after the optimization, the geometry is so complex that the traditional manufacturing process cannot be used to fabricate, and therefore it's necessary to use the additive manufacturing, to fabricate the parts. Because again, come back to the first point: design freedom. No matter what the structure, no matter how complex the part is, and by using the additive manufacturing process, you can fabricate the part. Of course, it's not an universal manufacturing process. So it means that not all case the additive manufacturing can fabricate, but generally speaking, it can be used to fabricate the freeform designed part. It has some limitation, but I will talk to you a little bit more details in probably chapter 5 and chapter 4, because it depends on the ability of the technology itself. So for example, we have talked about the roughness of the surface, cái độ nhám bề mặt chẳng hạn. Nó có thể chế tạo được chi tiết có hình thù bất kỳ, độ phức tạp cao như thế nào cũng không làm khó được cái additive manufacturing. Tuy nhiên nó cũng có những cái giới hạn nhất định của nó. Tôi lấy không phải cái gì cũng chế tạo được. Tôi lấy ví dụ như là về cái độ nhám bề mặt chẳng hạn, thì cái độ chính xác của cái bề mặt nó thường không cao. Cái surface roughness của nó là lớn hơn 10 micromet so với cái phương pháp gia công truyền thống có độ chính xác cái độ nhám bề mặt nó chỉ khoảng 1 micromet thôi. Thì rõ ràng cái anh additive manufacturing này không bằng rồi. Thế tuy nhiên thì chúng ta có thể áp dụng cái post machining sau đó thì chúng ta vẫn có thể, đúng không ạ, tạo được cái surface quality như yêu cầu, mà chúng ta lại chỉ cần gia công có một lớp mỏng thôi. Nói cách khác là chúng ta tiêu tốn vật liệu nó cho quá trình gia công nó thấp, hao phí máy móc cho quá trình gia công nó cũng sẽ thấp, và hao phí nhiên liệu năng lượng cho quá trình gia công nó cũng sẽ thấp theo, dẫn tới là hiệu quả quá trình nó sẽ tăng lên. Thì tuy nhiên là bây giờ thì tại cái thời điểm hiện tại thì nó cũng giống như mua một cái iPhone đời mới chẳng hạn, nó vừa mới ra nó sẽ rất là đắt. Nếu các bạn thử để khoảng 3-4 năm sau, đúng không ạ, thì nó sẽ rẻ đi rất là nhiều. Thì cái quá trình này nó cũng như vậy thôi, nó đang phát triển, nó đang rất là mới. Từ cái yếu tố vật liệu, yếu tố công nghệ máy móc nó sẽ rất là đắt, nó phát triển dần rồi, dựa trên những cái lợi thế sẵn có, cái phát triển dần thì nó sẽ chỉ có rẻ đi thôi. Thì lúc đấy đến một thời điểm đó thì nó sẽ đưa áp dụng một cách rộng rãi ở trong các ngành công nghiệp. Hy vọng là sớm tới đây thì nó sẽ sử dụng rộng rãi hơn nữa trong lĩnh vực hàng không, bây giờ đang dùng rồi. Ok. Product dematerialization. Okay, this term. Okay, so this means that you reduce the amount of used materials. So yes, because you optimize geometry, you eliminate the unnecessary material for the design. So after the fabrication process, so you have the lighter structure. So it means that product dematerializations, or you have the lighter structures. Simplify the exam line and product and components. So this is one of the advantages during the designing process. I do not remember which chapter I will show you. I can show you this, but generally speaking, for the traditional parts, so part is something that cannot be divided further. Yeah. Yes. So people fabricate the parts, and afterward they assemble together to make a component. With using additive manufacturing, sometimes you can combine different parts during the design process. And once you combine the parts together, so you have a little bit more complex components. So there's no problem with using additive manufacturing to fabricate complex components. But if you use the traditional manufacturing process to fabricate more complex components, means that the price will be higher. So by combining different parts together in order to fabricate one complex part, so you reduce the assembly process, or you simplify the assembly process. You save time for the assembly, of course, and in doing this, you can reduce costs, of course, and it's easy to control. Maybe easier to control the qualities through the simplifying assembly. Yeah, maybe it depends, because once you have the freeform shape, so it's a little bit difficult in order to check how accuracy the surface is, for example, because it's not a flat surface, it's not a regular surface, but it's a very complex surface. So again, you have another problem of checking the accuracies of the surface. In other words, it's a challenge. To reduce the time between design and manufacturing, the point is quite clear. Why? Because AM, you work with now is the digital era, kỷ nguyên số, phải không ạ? Digital era. And with using additive manufacturing, I have talked to you that we can use different kinds of computer-aided design software in order to design. We can use the FE software in order to virtually inspect the performance, the part. We can take both the single cycle or the multi-cycles. Yes, you can predict the stress strain distribution and so on. In other words, you can somehow see the performance of the part virtually before you prototype the parts or before you fabricate the parts. And in doing this, you can save cost and time during developing the parts. Yes, because when you check it virtually, you can somehow confirm that the part can work okay or not. If not, and then you can improve with the computer aided design. Yes, and check it again. So if it's fine, yes, with the with a certain safety factor, yes, and then you subject the part to the fabrication phase, and then if you test at that time, yes, it reduced the risk. It reduced the risk of failure. Everything, yeah, you still have some amount of percent of failure, yeah, of course, despite of the fact that you check everything okay virtually. But yeah, life is life, nothing is perfect. It's perfect. Okay, so where am I? Review time. Okay, improve product functionality. Yes, this is somehow linked with the exam line, because improve product functionality. So it means that if you want, you can combine different parts together to make one complex part. So generally speaking, each part will corresponds to a certain function. So when you combine them together, so one complex part, after the combination process, will have different functionality, or you can say improve product functionality. Yeah, you may say like this, or improve product functionality, improve product durability. Yeah, to a certain extent, to, ở một cái mức độ nào đó, to a certain extent. Because if we talk about if we talk about the the rapid plasma deposition, so the NOS rapid plasma deposition in Norway. So yes, they prove that their technologies is somehow similar to the forging process. I mean, the part quality can be comparing with the part which was made of forging process. But for the others, this it depends. For the other, we cannot confirm that. Yeah. So in general, we can say, upgrade ability through modular design. Yes, because when you design the part and you still have the connection with your customer, for example, and if the customer requests you, to modify the part, and you can upgrade, you can somehow improve through the design. You can add some geometric feature to the part to improve functionality or to improve the durability with respect to the previously designed structure. So you can do that. Yeah, you can do that during the modular design process, because now it's not something that you fabricate. It's something that you design with your computer. Yeah, so you can freely modify as soon as it's done before. This is done before you prototype the part. Cái vấn đề ở đây là các bạn có thể upgrade, đúng không ạ? Chỉ cần là khi nào mà các bạn vẫn làm việc với máy vi tính, đúng không ạ? Chúng ta có thể, nếu mà khách hàng yêu cầu các bạn là improve cái functionality nào đó, thêm một cái chức năng nào đó, hoặc là thêm một cái features nào đó, cái đặc điểm, cái cấu trúc nào đó vào trong cái part, thì các bạn hoàn toàn có thể modify ở trong Inventor, SolidWorks, CATIA gì đấy. Chỉ cần là gì, chúng ta làm trước khi mà chúng ta in cái sản phẩm đó ra. Chỉ in rồi mà modify đi thì có nghĩa là cái sản phẩm cũ nó vứt đi còn gì nữa đó, and so on. However, yes, there are some points highlighting the product redesign advantages of the additive manufacturing. But together with these advantages, you also have challenges associated with the phase of product redesign. Firstly, regarding the educational designer, educational designer. Uh, so you need the designer with a certain level, or you need to educate the designer and engineer about the benefits of AM. It's somehow like a horse running on the own road. So if the horse is familiar with the road, so he does not want to run on the other road. So if the designer or the engineer are familiar with the traditional design process, so how to persuade them to follow the new design process to create the, how can I say, the good performance pass with having the light weight, for example, to be able to apply to the airplane. So this is a matter of education. So to change the mind, it's not easy because the trade and the manufacturing process have been being developed for 100 years. It could be more than 100 years because it depends on the industrial revolution. Cách mạng công nghiệp thì nó diễn ra vào 1800 bao nhiêu tôi cũng chả nhớ nữa, nhưng mà đại khái là đấy, nó những cái quan điểm thiết kế là nó phát sinh ra từ những cái năm mà xảy ra những cái cuộc cách mạng công nghiệp rồi cho đến bây giờ. Thì những cái gọi là traditional manufacturing process, nghĩa là cũng như là traditional design process chẳng hạn, thì những cái mà nó đã diễn ra cả trăm năm rồi, rất là khó để mà thay thế cái tư tưởng ấy được. Trong khi đó là cái technique cũng như là cái optimization assisted design process thì nó cũng mới introduce vào cái gọi là đưa vào cái thị trường và đưa vào cái giới học thuật gần đây thôi, gọi là gần đây cũng chắc phải 20-30 năm rồi. Supporting the skill development of design and engineer. Yes, so this is master of education and training. So you must be trained in order to use the design software, to use the how to handle with the powders materials, for example, because it's quite detrimental to human health, and some is very dangerous. So for example, the aluminum powders. So if there is a static discharge, tia lửa kiểu tĩnh điện ấy, là nó cháy nổ ra luôn chứ không phải là. Yes, and for example, magnesium powders alloys, when it exposed to the environment, so it can be burned. And so how to store in the appropriate manner the feedstock materials, how to handle the materials, how to use the 3D printer properly, how to design the part properly for the 3D printing process. So all the things need to be, how can I say? So these things need to be introduced to the engineer or designer, and they need to be trained so that they can perform the work properly. Integrating sustainability consideration to using the design for environment or eco design principle. Yes, of course. Yes, sustainability consideration. So practically, if you consider the design near nature part, design and fabricate near nature part by using the additive manufacturing, so it means that you design and you fabricate the part having the shape close to the final shape of the part. So you save a lot of materials during the manufacturing process, because if you the cutting process from the billet, so you eliminate a lot of surrounding material until you have the final part. If you design and if you fabricate the near nature part, so the amount of material which will be eliminated afterwards will be reduced. So in other words, you save the materials. So I have talked with you these points several times. Yes, Anna. Yeah, someone want to join in the class. I guess that someone raised their hand, or his hand or her hand. but no. But for example, okay, and now, or let me consider one case. So, for example, if we are talking about the hydrogen-powered vehicle, so now the car runs with the fossil fuel like the gasoline, like the diesel oil. Uh, yes, uh, you know, the several authorities have encouraged their citizens to use the cars run by the renewable energies, because if the cars run with the fossil fuels like the gasoline and and the diesel oil, and the amount of carbon, the CO2 carbon dioxide emitted into the air will be higher, because the number of the car uh, increase year by year. Yes, every year actually, because the transporter increase. And in order to save the environment, yes, the many authorities in the world, especially in America, in the European countries, in several developed country in Asia, for example, in Japan, in Singapore, and in Korea, they promote the citizen to use the cars run by the renewable fuels. Renewable fuels, like for example, the ethanol combined with the gasoline, or they can use the how can I say, the energy from the sun, photovoltaic kind of battery, kind of battery. So the energy from the sun, which can be used to convert to the electricity in order to run the car, or they can use the hydrogen, yes, as the burning fuel, as the fuel. So let's say if we design the hydrogen storage system, yes, and we use the uh, how can I say, uh, computer aided design process. We use the additive manufacturing, so you can contribute to the way to shape the path toward a sustainable futures. Why? Because the first thing is that you design and you can optimize the part of the system, which can be equipped in the car or in the plane in the futures. Who knows? The system use the hydrogen. So, for example, this is the renewable fuels, renewable energies. So is quite friendly to the environment, because the bypass is the water. It's not the CO2, it's not the NOx, it's not the NOx. That is something which is friendly. How can I say, friendly to the environment, which is friendly to the environment. Yes, and yeah, and that's the point. And that's the point. So even if the number of the vehicles increase, and if we can optimize the structures to reduce the weight of the structures, we can fabricate in the net shape component. We can use the renewable energies. Yeah, we can go forward to a more sustainable futures. So that's why we should integrate the sustainability consideration during the design. Design is mean that you optimize the shape, you eliminate unnecessary materials, yeah, eliminate unnecessary material at the low stress areas, or you can yeah, combine different parts together to make a complex component, in order to reduce the assembly steps afterward, for example. So you can reduce the energies during the assembly process, and you can consider also the utilization phase, where you use, for example, the hydrogen fuel, yeah, to save the environment, and so on, and so on. So yeah, so AM MC manufacturing is just one of the manufacturing processes, one of the manufacturing process. So everything, yes, can be fabricated by AM. So if you can use AM, so why not? Because it has the possibility to contribute to shape the path toward a more sustainable future. Yes. certifying a new component. So yeah, it's difficult because the reliability, yes, is not so clear. Yes, and therefore we have a challenge in certifying the new component. Yeah, capturing and replicating learning in future application. Yeah. So let me talk a little bit about the material input processing. Improve the resource efficiencies of raw materials. Yes, yes, because we, like in the case of direct energy depositions, if we need to synthesize the materials layer by layer, so at export, the material will be deposited too, and the energies will be irradiated as well. And then you melt the material, and the material can be solidified afterwards and connect with the welding line and connect with the previous layer. And we have the near shift part, and therefore we improve the efficiency of resources, nghĩa là tận dụng cách hiệu quả, nâng cao cái khả năng tận dụng cách hiệu quả các cái vật liệu đầu vào, nguồn vật liệu đầu vào. Reduce toxicity of material processing. Yeah. Localized material recycling. Yes, because after the 3D printing process, especially for the case of powder bed fusion, you can collect the residual powders. You can collect the residual powders or the overflow powders, and you can consider these powders for reusing. Yes, firstly, we will need to eliminate the agglomerated powders. So those powder which are already attached to others will be eliminated based on their size. So they use the sieving process, sàng lọc, to eliminate the large powders, and then these sieved powders can be reused. Yeah. But please keep in mind about the properties of the materials under the influence of the heat during the building process, and depending on the quality of the part, and depending on the yeah, mostly regarding the quality, and you can determine whether you can reuse or you should recycle the powders. Diversion of waste and byproduct from the waste stream, upcycling waste material into a new application. Yeah. Okay, just some information about the input processing. So we do not focus on process and fabricate the input material. So for example, water atomization, to fabricate, to synthesize the powders. No, we do not focus on this. We can introduce, we can discuss briefly about these technologies in order to synthesize powders, but we not focus on, and we do not go into details. Oh, this is many than I expected. And let me see, we have a component, because here is the advantages and challenge is how can I say, we consider these advantages and challenges from the design process, from the materials, for the manufacturing process, for the utilizations, it means product use, repair, and recycling. So the different phase of product development, product yes, starting from the material, from the design to almost the damaged parts for recycling. So the whole process, uh, how can I say, product life, the whole product life. So every phase will have certain advantages and disadvantages regarding additive manufacturing. So I think that we should Just have a pause for 10 minutes first. Yeah. I'm a little bit overloaded for the moment because yes. Okay, see you in 10 minutes.